Welcome to this session of predicate logic. Till now, we have seen what is meant by predicate logic. We have seen what are quantifiers. We have seen how do we nest quantifiers. We have also seen how do we negate the quantifiers. In this lecture, we are going to see the quantified rules of inferences. If you remember the rules of inferences that we talked about when studying propositional logic included modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, addition, simplification, conjunction, etc. So they were the rules of inferences as they are applied to the propositional logic. Now today we are going to see the rules of inferences as they are applied to predicates. Right? So let's start. The various rules of inferences, quantified rules of inferences are, we have universal instantiation which says for all x, p of x, if px is true for all values of x, then p is true for a particular value c. C is some particular value. Let us say the universe of discourse, this x is a value from the universe of discourse. The x is a variable which is taking the value from universe of discourse, and c is some particular value of x. So we say if p is true for all the values of x, then p is true for a particular value of c. Say for example, if we say let us say if I say for all x, px, where px says all men are mortal, then this is true for, let us say, a particular x is equal to, let us say, John. We can say John is mortal. If p is true for all the values of x, then p is true for a particular value of x. This is universal instantiation. We have created an instance of the universally quantified predicate. Then we have universal generalization. If p is true for any arbitrary c, if I can say that p is true for any arbitrary c, any arbitrary value that I might choose from the universe of discourse, if it is true for any and all arbitrary values, then I can say that px is true for all the values of x. Here I was specifying. Here I am generalizing. Here I was converting a generic statement to a specific statement, and here I'm converting a specific statement to a generic statement. That's what's called universal generalization. Then we have, if px is true for, let us say, some value of x, then we say that p is true for that some value c. If c is the value for which px has been identified to be true, then we can write, if for all if there exists x for which px is true, then if c is that value, then p of c is true. This is existential instantiation. I am creating an instance of the predicate. Then the reverse is the generalization. If p of c is true for some element c, I cannot say for arbitrary c, I am saying it for some element c, then I can say that p of x is true for some value of, or there exists a value x for which px is true. Right? So they can be understood as universal instantiation is the rule of inference used to conclude that PC is true where C is a particular member of the universe of discourse, given that the premise for all x px. If for all x px is true, then if C is a particular member of the universe of discourse, this is also true. Say for example, all women are wise, then Lisa is wise, where Lisa is a member of the universe of discourse of all women. So I am creating an instance of the word all. The word all here is being instantiated in Lisa. Universal generalization is the reverse, which says that if for all x px is true, given the premise that pc is true for all elements c in the universe of discourse. It is used when we show that this is true by taking an arbitrary element c. If I can take an arbitrary element c, then showing that pc is true, then we can say if the element c that we have chosen is truly arbitrary and not a specific element. If it is a specific element, then we'll have to go for existential quantification. But if it is an arbitrary element, then we can see, if we can say that if pc is true for an arbitrary element c, then for the universe, for all values of x, px is existential instantiation. It says if px is true for a value of x, for some value of x, and if that value of x is c, and if that value of x is c. See, the important point is we cannot select an arbitrary value of c. We must be a this must be a value c for which pc is true, right? So if there exists a particular value c that I can choose, then I can say that if there exists a value x for which px is true and c is such a value, then pc is true. And the reverse is the generalization. If I can identify a specific value c, not arbitrary, specific value c, if there is one element, there is at least one element c in the universe for which pc is true, then I can say that there exists an element x for which px is true. I can define universal modus ponens and universal modus tollens. I can do without defining them also. See, if I have for all px, sorry, for all x, px implies qx, right? So what I can do is I can first apply universal instantiation to get, let us say, p of c implies q of c, and then if I have another, suppose this again I have for all x px, so it will be instantiated as p of c. Now this is a proposition, this is a proposition, so therefore I can say q of c, which can then be universally generalized as for all x q of x. But not necessary to do it. I can write it in a generalized manner as for all x px implies qx. If p is true for a, then q is true for a. This is the universal modus ponens. Similarly, I can define universal modus tollens, which says if px implies qx is true for all values of x, and if q is false for a particular value a, then p is also true for that, false for that particular value a, right? So these are universal modus ponens, universal modus tollens. Similarly, I can also define universal hypothetical syllogism. Please understand, I cannot define existential modus ponens or existential modus tollens. They cannot be defined. Modus ponens or modus tollens will only work for universal quantification. Similarly, the hypothetical syllogism can also be defined for universal quantification. Once again, existential I cannot define. Only for universal quantification I can define hypothetical syllogism, also called universal transitivity. If px implies qx is true for all x, qx implies rx is true for all x, then I can say for all the values of x, px implies rx. Let us see how we can apply these quantified rules of inferences in verifying the or validating the arguments. Let's take a simple example. Everyone in this discrete mathematics class has taken a course in computer science. Maria is a student in this class. These are the two premises. Let us say this premise 1, premise 2 imply the conclusion Maria has taken a course in computer science. Now, let's define dx denotes x is discrete mathematics class. Cx says x has taken a course in computer science. Now the statement everyone, when I am using everyone, that means I am using universal quantification. Everyone in discrete mathematics class has taken a computer science course. That means for all x, if x is in the class, then x has taken a computer science course. So I have for all x, bx implies cx. And then Maria is a student in this class. That means I'm using instantiation over here. Maria is an instance of bx. That means b Maria. So I have one premise, two premise, right? So I can say for all x, bx implies cx. This is the premise. Now this can be instantiated for Maria. If Maria is a student of this class, then Maria must have taken the computer science course. Because I say for every person, if the person is a student of this class, then the person has taken the CS course. So if Maria is a student of this class, then Maria has taken a CS course. And the second premise says Maria is actually a student of this class. So by modus ponens on these two, I can say Maria has taken a CS course. Let's see another example. Students who pass the course either do the homework or attend lecture. Students who pass the course either do the lecture, either do the homework or attend the lecture. That means if a student has passed, see, please note the language. It is saying if let us say pass the course, let us say this is px, homework let us say hx, lecture let us say lx. What it says is if a student has passed the course, then that student has either done the homework or attended the lectures. That means for all x, px implies h of x or l of x. That means for all the values of x, px can only be true if h of x is true or l of x is true. So this is my first premise. Bob did not attend every lecture. So L Bob. This is instantiation. So this is my second premise. Bob passed the course. P Bob. This is the third premise. This is once again instantiation of Px. So Bob is a person. Bob is a value that I am putting in the variable x. So I have for all x, px implies hx or lx. This is the premise or the hypothesis. So I can say p Bob implies h Bob or l Bob. If Bob has passed, that means the Bob has either done the homework or Bob has attended all the lectures. Now I know Bob has passed. This is given in the premises. So that means I can apply modus ponens over here. It means Bob has either done the homework or Bob has attended all the lectures. Now the next premise says Bob did not attend every lecture. Negation of L. So negation of L. This is again the premise. So HB or LB. And this is L negation of LB. So disjunctive syllogism. See, H of X was a predicate. H of B is a preposition. All the rules of inferences that we have studied earlier will apply on the prepositions. So if I say HB or LB and negation of LB, I can apply disjunctive syllogism to say HB. So that means Bob must have done the work. This is the conclusion. A student in section A of the course has not read the book. Everyone in section A of the course passed the first exam. Can I use these two statements to imply someone who passed the first exam has not read the book? Now see, a student, that means existential. Everyone, that means universal. So if I define AX to be X is in section A, BX to be X read the book, and PX to be X passed the first exam. So now the premises become there exists a student X such that X is in section A and X has not read the book. There exists X such that AX and negation of PX. Everyone in section A has passed. For all X, AX implies PX. And the conclusion, someone there exists who passed the first exam. If he has passed, then he has not read the book. So this is the conclusion. How do I check it? Now once again, I have these premises. This is the hypothesis or the premise. Now first of all, what I'll do is, let us assume there is a student. Let us say A. A is, let us say, a student. Right? Let's call him Adam, denoted by, let us say, A. So if there is a student X for which AX and negation of BX, let us say that student is Adam. So Adam is a student of section A and Adam has not studied the book. Right? This is and. So I can apply simplification. Now this has become a proposition. This was a predicate. After simplification, after instantiation, it has become a proposition. So I can apply simplification. I can say Adam is a student of section A. Now, second hypothesis says if X is a student of class A, then X has passed for all the values of X. So Adam is such a value. So if Adam is a student of section A, then Adam has passed the course. And we know that Adam is a student of section A. So by applying modus ponens, I can say Adam is a student. Adam has passed the course. Now, Adam has passed the course and Adam did not study. So PA is true. And once again, I had Adam is a student of section A and Adam has not studied the book. That means by using simplification, this is also true. So Adam has passed. Adam did not study the book. So I can apply conjunction. So I can say PA and negation of BA. So now, if this statement is true for Adam, if this statement is true for Adam, that means this statement is true for at least one student from the universe of discourse. So I can apply existential generalization. So that means there is a student or there are some students who have passed the course but who have not read the book. That was the conclusion that we started off to verify. Let's see another example. Check the validity of the following argument. All animals are mortal. All human beings are animal. Therefore, all human beings are mortal. Quite simple. Let us define Px to be X is an animal, Qx to be X is a human being, Rx to be X is mortal. So this first statement, all animals, see all. So universal, all, universal, all, universal. Right? So my premises are for all X, Px implies Rx. For all X, Qx implies Px. All animals are mortal. P implies R. All human beings are animal. Q implies P. And the conclusion is all human beings are mortal. Q implies R. It's a straightforward case. So this is the given premise. Let us say once again, let's take Adam. Let's again disturb Adam. Let's say Adam is a person whom we are talking about here. So Adam, and denoted by, let us say, A. P of A implies R of A. If I say all animals are mortal, let us say Adam is an animal, so Adam is mortal. Then again we say all human beings are animals, right? So once again I can say Adam, all human beings. If Adam is a human being, then Adam is an animal. Here I am saying if Adam is an animal, then Adam is mortal. If Adam is a human being, then Adam is an animal. So I can apply hypothetical syllogism on these two to say this. See, Q implies P and P implies R. So this means Q implies transitivity. So Q implies QA. If Adam is a human being, then Adam is mortal. And as we used universal generalization, instantiation over here, so I can say, I can apply universal generalization over here to say that Qx implies Rx is true for all the values of x. In other words, all human beings are mortal. So this was all about the predicate logic. I hope you have understood the concept of predicate logic. If there are any doubts, you can always ask me the doubts through comments or through direct messages, and I'll try to resolve your queries. Right? Till the next time, thank you.